It's nice to be back to this very beautiful place where so much mathematics in our field has been done. So I want to explain to you a bit why we have been thinking about Davydov-Yetter cohomology and what kind of tools we were developing. And actually, I want to show you that it's very profitable to consider the appropriate coefficients for Davydov-Yetter cohomology. This gives computational tools and it allows you to prove things which are in principle proven, like Ogneano rigidity in a slightly more general setting. And then I will show you in the end a tool which makes it really computable and has links to conformal field theory. Because let me briefly say what my personal motivation was to look at Davydov-Yetter cohomology. It's by now very well established that if you study a two-dimensional conformal field theory, the following data are important: a modular finite tensor category, and these days modular doesn't mean necessarily semi-simple, so it can be non-semi-simple, and a pivotal module category over it. And I won't have to say a lot in this talk about the words modular or pivotal, and I will comment on this at the very end of the talk. In this situation, there is a rigidity, there's a dichotomy. If in the semi-simple case, we expect rigidity, absence of deformations, and there are many such results. So there are finiteness results, how many fusion category structures you can find on a fusion ring, if there exist such structures at all. And on the other hand, if in a non-semi-simple situation, which becomes interesting in CFT due to the logarithmic CFTs, there are cases known where you can find infinitely many non-equivalent rigid tensor structures, so you can deform tensor structures. You find families of module categories, and what we want to do is we want to study them infinitesimally in the spirit of deformation theory. And the idea in this talk is to get tools for actual computations in actual models. Maybe that's a bit of an old-fashioned approach, but it has still its values. And I want to explain Davydov-Yetter cohomology. Now, let me start with something which is, in a sense, algebraic kindergarten, the Hochschild complex. And so if you want to deform the multiplication of an associative algebra, what you should keep in mind is that associativity is an equation. So by working over the dual numbers, we effectively linearize this equation, and it is profitable to see this equation as the equation for a two co-cycle in a chain complex, co-chain complex, the Hochschild co-chain complex. And probably everybody has seen this. Let me just emphasize for later comparison that here we have multiplications and the differential squares to zero because of associativity. Now, the insight, which is also technical insight, is that lower cohomologies have classical algebraic interpretations like centers, derivations, and second Hochschild cohomology is infinitesimal deformations. All deformations will be infinitesimal, and the third Hochschild cohomology obstructions. And finally, let's recall why it is so nice to have Hochschild with coefficients which are bimodules. Well, that's because it automatically leads you to complexes like bar complexes, which are very big in practice, but helpful for theoretical purposes. And it also allows you to understand what better, shorter, more tractable resolutions are. And we get long exact sequences, which are, of course, fantastic tools. Now, what is the setting of this talk? Well, in this talk, all categories will be finite k-linear categories, and I will, at some point, when I use certain things about the linear product, which the experts will realize, I will assume that the field is perfect. It could be generalized. So all monoidal categories will be finite tensor categories. All categories will be finite categories in the sense of, in the presence of Dimitri, I can say the book. And In particular, monoidal categories will be rigid. So what are deformations problems you want obviously to consider? Well, we want to study deformations of the associator, and look, our game is as follows. I'm only deforming very few things. I'm not deforming the category as a category. Yeah, I'm not deforming here the tensor product as a tensor product. These are valid questions. I'm deforming in a sense just at the top level of the morphisms. And there I have equations. Obviously, I don't have to show to this audience the pentagon equation. It's a nonlinear equation. And we want to study deformations of the associator, where we use the dual numbers, and we get a complex, and we get an equation which we want to study as the equation on a 3 cocycle in a complex built from the tensor category. And I'm formulating the deformation problems in a very sloppy way. Of course, there's a much better framework. And if you want to see more about this framework and results also on deformations on tensor categories, Marcos Seto has a poster which is about to be printed, as far as I understand. So it should be around soon. So, okay. Another thing you could deform is a monoidal functor. Well, a monoidal functor comes with additional data. These are the monoidal constraints. Actually, I will tacitly go from monoidal functors to lax and oblex monoidal functors at a given moment, but this is not the big point of the talk. It obeys also a nonlinear equation, and it is reasonable to study deformations of these constraints, and they will be 2 cocycles in a complex built for a monoidal functor. That's Davydov-Yetter cohomology. But before doing this, let me mention why this is so interesting. Well, everybody here, I guess, knows that a module category amounts to having a monoidal functor from C into the endofunctors. And also there's an old and important result that if you want to deform a braiding, then you can alternatively study monoidal structures on the tensor product. I modified here slightly the tensor product by looking at the induced functor on the delinear product. And if you look for a monoidal constraint here in this equation, then you see that if I take the tensor product here, and if I take this in the other way, then y1 and x2 and y1 change position. That's why it's related to the braiding. You need a bit more care to state the relation carefully, but everybody can work this out. So it's interesting to deform monoidal functors. And Davydov-Yetter, the Davydov-Yetter cochain complex is a cochain complex associated to such a monoidal functor. There's no joint paper by Davydov and Yetter. And I guess there will be never a joint paper between Davydov and Yetter. So it's independent work, and both deserve credit. So what we do, well, the cochain complex is defined on, well, we are working in a k-linear setting, on a vector space of natural transformations. I want to keep notation. Oh, what this is? Yeah, okay, yeah. I want to keep notation light. So I'm assuming that the tensor category is strict. And then you see these are natural transformations. You apply the functor here to each of the n tensorons, and then you tensor, and then you're looking for endo transformations. That's a vector space, a finite dimensional vector space. And then you write down a differential, and the differential has, very roughly speaking, it looks very similar to a Hochschild differential, but here instead of a product, you have a tensor product. And we will see that this is actually Hochschild in the appropriate setting. This is also not a new thing, but it's an easy exercise now to check the deformations of the data are 3 cocycles for the identity, and deformations of the monoidal functor are 2 cocycles. Well, in order to see what the right coefficients are, it's interesting to rewrite it as Hochschild cohomology. And the first observation is the following one. If C and D are tensor categories, and you can, in nice situations, and we are in a nice situation, endow the category of functors with a tensor product, which is called the Day convolution. So this is defined in terms of a coend, and here it is weighted by the home spaces, and it is weighted. This category of functors, not monoidal functors, but of functors becomes monoidal. And if you are in a monoidal category, you ask what are the monoids in the monoidal category, and the monoids are just lax monoidal functors. This is an exercise which, if you find the rest of the talk boring, you can try to do in your head. Yeah, so but this is the observation. So monoids are lax monoidal functors, lax because we've just a multiplication. Observation 2, Davydov-Yetter for F, which is now a monoid, is Hochschild internal in this monoidal category. And observation 3, coefficients are then bimodules. And if you work out what a bimodule is, it is an object in this category. So it is a functor, but it has a left and a right action. And that amounts to having here constraints. And we can characterize this functor by its value on the monoidal unit, which is an object in D. And then we have constraints here, and we have constraints here, which show that the essential information amounts to having an object in the target category D and half braiding. Yeah.
So what does Hochschild internal mean? So you can do the Hochschild resolution.
Yes, and you are writing down homes in the category. This is in principle also things you can read in textbooks in a different language. Yeah, so I'm writing it in this way because in the end I want to make a comment. Yeah, so so if you go to what I call the book, then you will find it in a different way. Yeah. Okay, so which means we should look at the following category. So if we take, we are given a monoidal functor, and then we have a half braiding relative to F, which is a way to put images under F from one side to the other, and of course a hexagon has to be obeyed. Yeah, so and then we look at the category consisting of these objects for a given monoidal functor, and the morphisms are compatible with the half braiding. Of course, everybody here has seen this in special cases. Take F to be the identity, and you're getting back to Trinfeld center. Yeah, it's a generalization of the Trinfeld center, and that's where you should look for the coefficients. Good. So now, let's introduce the following complex. So we introduce two coefficients. They're both x and y are both elements in this generalization of the Trinfeld center. And then we introduce now cochain vector spaces, which are natural transformations. Before we didn't have the x and the y. I'm realizing I shouldn't do this because online participants cannot see this. Yeah, so
they can.
okay, they can.
With the laser pointer, they see it. Yeah.
Okay, good. Yeah, good. So the differential now is a generalization of the differential here, and I find it a bit more instructive to look at it graphically. So you see, we have, as usual for Hochschild, we have a boundary term, we have another boundary term, and then we have terms in the middle where we reduce the number of inputs by taking tensor products. And here, for the boundary terms, we are actually using the half braidings to get terms which are correctly typed. And you have to check that it squares to 0, but this is not a hard exercise. Then the next thing you do is you sit down and you look for concrete interpretation in low dimensional degrees. And what you see is that in degree 0, you find those elements in home D, which are also morphisms in Z of C. You know that morphisms, which are morphisms in the Trinfeld center, are characterized by equations. So these are the objects which are characterized by the morphisms which obey these equations. H1 of F gives natural transformations, which are compatible with the monoidal structure. Obviously, this should know about the monoidal structure, modulo some notion of inner derivations, and what inner derivation can be read off from the complex. And H2, the second cohomology, gives first order infinitesimal deformations of the monoidal structure. And at this point, yeah, you're happy because you know in principle how to access deformations of brainings, deformations of module categories, all interesting stuff, including in concrete situations. You're maybe not so happy if you think about how this complex is defined, because handling natural transformations is a bit cumbersome. Yeah, so we need to think about this. Okay. But what are the goals we have very concretely here in this talk? We want to understand Davydov-Yetter cohomology, at least to the extent that we can compute dimensions, including in concrete examples. And we want to be able to determine explicit cocycles, in particular 2 cocycles, so that we can write down explicit deformations. And which hopefully one day will be explicit deformations of conformal field theories. Yeah? So, and I will give you a hint on this at the end of the talk. Computing dimensions will be that we aim to translate the question of computing the degree of a cohomology to some representation theoretic computation, because that's in the end a good setting where you can do computation. Okay, good. So to this end, we have to rewrite Davydov-Yetter cohomology, and I will rewrite it in 2 ways. I will use really old-fashioned cohomology theories, which you find in textbooks, which were written way before most of the participants were born, including, and the basic work has been even written before I have been born. So we are using fancy methods. I still think they are useful. And I want to give you a proof of Ogneano rigidity based on these insights, and then we move on and provide additional tools. Okay, so this is a very well-known and useful fact, which should appear in more category theoretic books. So natural transformations can be written as an end. An end comes with structure morphisms. Structure morphisms are the components of the natural transformation. And the end implements the conditions you have on the naturality squares. Well, let's do a simple calculation together, just for the fun of it. So the natural transformations can be written as an end. I'm working in a setting where the category is rigid, so I'm using rigidity to put x1 from the covariant into the contravariant argument, x2, and all this. Then I'm realizing that here I can take the end inside the argument of an hom as a co-end. Well, this is just that hom is a left exact functor and commutes with these limits. Now, you see, oops, this guy here is a good old friend, because if we are working on a tensor category, and here find a tensor category in my case, we can set down endo functors, which are given by this co-end, and we are sandwiching the argument between x dual and x. And this is a very interesting endo functor. It is more than an endo functor. It is a monad. It's more than a monad. It is a Hopf monad. So think about this as a replacement of a Hopf algebra in D. So it has a lot of structure. And in this simple case, you see that the Eilenberg-Moore category is exactly the Trinfeld center. So this the corresponding adjunction is monadic. And we have here reformulated the natural transformations, which are the co-chain groups in Davydov-Yetter in terms of this monad. I'm doing this here in the simplest case, but of course you sit down and you generalize this. And if you have here a monoidal functor, you can introduce also this endo functor. And this is called the central monad of the monoidal functor F. It is a Hopf monad as well. So a Hopf monad is an endo functor which is op monoidal. And its Eilenberg-Moore category can be computed. And the Eilenberg-Moore category is our friend, the generalization of the Drinfeld center. So let me summarize the situation. We have here the Drinfeld center, the generalization of the Drinfeld center. We have a forgetful functor which forgets the half braiding. It is exact and monoidal. So its left adjoint is left exact and op monoidal. Then if we compose this functor and we go down, we get an endo functor on D. This is the Hopf monad, which is op monoidal. And we get also a co-monad here by first applying U and applying F. That gives an endo functor on G, which is a co-monad. And we will use all of them in a very standard way. So if you are given a co-monad on a category C, and C will be our generalization of the Drinfeld center, it gives rise to a bar resolution. And the bar resolution is very obvious. So if you know what an adjunction is, you see it right away. So you are applying G, you're applying G several times, and then you get from the co-unit of the adjunction by applying them at various spots, you are getting the differential via an alternating sum. And the theory is fully developed. So at that point, you know, if you have a notion, what is a G projective object? Well, it is a G projective object is characterized by the fact that it is a retract of a free object. Yeah, so, and then there's a notion of a G exact sequence, and then if you have a notion of a G exact sequence, you have a G resolution. So we take a projective resolution. So we take G projective objects, and the sequence should be exact. I should point out that G projective is not exactly the same as projective, right? So we have to be a bit careful about this. But I'm not bothering you in the first talk of this morning with too many technical details. Yeah. So okay. Then you have a bar resolution. This turns out to be G projective. And then if you are given a functor from C to D, you can use it as a coefficient to define the homology of X, and cohomology similarly by applying the functor to this complex and measuring the cohomology. And all this is in principle so easy and straightforward that if we are teaching advanced algebra, when we had the time, we could hear it. Yeah, and good. Now the observation is the following one. If we are given a tensor functor such that this central monad for F exists, well, this is true under our assumptions. And if we are given coefficients, then the Davydov-Yetter complex is isomorphic, not just quasi-isomorphic, even isomorphic on the nose to the comonad complex for the comonad given for the adjunction I've just exhibited. So here there is a way, if I had introduced more notation, how to identify the coefficients with the corresponding objects in ZF mod. It's just juggling notation. There's checking that the differentials are the same is a bit of work, but it's not work for a talk. Okay, so now let's see how we understand Ogneano rigidity in this case. And let's start with the following lemma. So if we have a tensor functor between semi-simple finite tensor categories, then this category which generalizes the Drinfeld center is also semi-simple. Why is this true? Well, we have a Hopf monad, so we could use, or we will use Hopf algebra technology. There's Maschke. So let's lose Maschke. So in this setting, there is also the notion of an integral. It is exactly what you expect it to do. So it is here, and it is a morphism, which if you compose it with the co-unit, obeys a compatibility with the multiplication. And if you write it down, you see exactly the integral. And if the Hopf monad would be tensoring with an Hopf algebra, it's literally the integral. So an integral is called normalized if applying the co-unit to it gives the identity, or the identity times a non-zero factor. And then the following is known. The central monad without without f has a normalized integral. This is a very simple calculation using quantum dimensions. There's not much going on because the integral is very explicit in terms of co-evaluations. And of course, you're using statements that quantum dimensions and sums over squares of quantum dimensions are not zero. And if you then you can check if you apply the monoidal functor on the integral, you get a normalized integral. So then Maschke works. And we know this category is semi-simple, so all objects are projective. We don't know at this point whether the objects are G-projective, because I pointed out projective is not necessarily G-projective. But there's a next lemma, which I'm just stating and not proving. So if you're given an adjunction which defines a comonad, and if the right adjoint in the adjunction is faithful, then every projective object upstairs is also G-projective. So yeah, these two notions coincide in our case. And now we can prove the following variant of Ogniano rigidity. So any tensor functor between semi-simple finite tensor categories, any choice of coefficients, then Davydov-Yetter cohomology vanishes for all n bigger than 0. Yeah, and strictly bigger than 0. And the idea is we are in a setting where you have the comonad, the monad and the comonad. Then the comonad cohomology has the property, which is again a textbook argument, just slightly adapted, that if the coefficients are G projective, then the comonad cohomology vanishes. So it just suffices to prove that all possible coefficients are projective. But we have shown that, well, we have here a forgetful functor, which is faithful. So the projectives and the G projectives are the same. So all objects are projective because the category is semi-simple, and we are done. So that shows you that these very big bar complexes have a certain merit to it if you want to understand things, but they are too big to compute. So we have to continue, and that's the second part of the talk. So we went from Davydov-Yetter cohomology to comonad cohomology. Now I want to go to also something which is old textbook knowledge. That's in MacLean's book on homology. There's relative cohomology, and that's what I'm going to use next. So this is the setting. So we have abelian categories. Then we have here an adjunction, and we assume that the functor u, which is the right adjoint, is additive, exact, and faithful. And the terminology is that we call this adjunction a resolvent pair of categories. And in our setting, such an adjunction is automatically monadic. But this is something I'm not going to use. It's just a side remark. Everything in the sequel will depend on the adjunction, but the adjunction will be suppressed in the notation. Yeah, so because it would be rather cumbersome to have this as an index. Now, what is the idea of relative cohomology? It's in a sense, we don't want the cohomology inherent to B to play any role. So what we say is that a morphism upstairs in A is allowable if for this morphism, the kernel, if I look at it downstairs, so U of the kernel of F is a direct sum of the U of the source of object, and the same for the image. And of course, everybody here has been working with relative cohomology. If you work in a linear setting, you're doing this, and then these conditions are not very deep.
What would be the standard example?
In a sense, if you want to do, the first example would be take Vogtschild and then take it for K algebras, and then you would do it for bimodules and vector spaces. Forgetful functor. We will apply it to an adjunction which was already on a slide, namely the adjunction which involves this generalization of the Drinfeld center and the underlying category D. And whenever you prove things in a homological algebra course for abelian groups, and then you apply it to vector spaces, you're secretly doing this. Yeah, we are not making a big fuss of it, but now here our category B might have interesting homological algebra intrinsically, but we shield it away. So then you define what is a relatively projective object, and everybody has seen this diagram. What I should point out is that here the surjection has to be allowable. G can be any morphism, but this has to be allowable because we don't want the homological algebra of B to play this into our game. Then you define what is a relatively projective resolution, and well, it will be a relatively projective object, and the differentials have to be again allowable. Yeah, so these are the good morphisms. And then given a resolvent pair and a relatively projective resolution, we can define cohomology groups, and this is the relative X group, and here this is the notation A comma B, which stands for the whole adjunction, obviously. Good. It's now textbook methods to show that if we have an allowable short exact sequence for the coefficients, then we get a long exact sequence for the relative X groups, and that's of course a fantastic computational tool. And everybody here in this room can prove it, and the proof is also in McLennan. Good. So now you are realizing that if we are working with an exact tensor functor, then we can, and with coefficients again, then we can rewrite Davydov-Yetter cohomology in terms of the relative X, and it is the relative X for the adjunction which I had on the blackboard. And we know that Davydov-Yetter cohomology groups are relative X's. Good. So we have, what did we gain? We gained long exact sequences. That's something I want to use and to show. And what we also gain is that we get Yoneda products, and we can write down n cocycles in terms of products of one cocycles. And this means we do not only know that there must be some deformations, but we can get the deformation data very explicitly.
What are Yoneda products?
Oh, the Yoneda product is the, you take X and you splice it together. If you take the Yoneda X, by which I mean extensions mod, the relation you have in mind, then you can put them together.
Thanks.
And at a given moment, you prove that this is also the product you get to the X group if you define it in terms of projective resolutions. Good. So now you can sit down and get some cheap results. So for example, you can prove that for every exact tensor functor, the first Davydov-Yetter cohomology vanishes. Well, that's a cheap result in the following sense that we know now that the first Davydov-Yetter cohomology is a relative X. For first cohomology, this is contained in the X1 for the monoidal unit, but we know that X1 vanishes for years. So in this case, we get automatically a vanishing result. So exact tensor products do not admit any differentials.
So do you assume a characteristic 0 or?
Yes, I should have written it down. Yeah, but I'm assuming that this result holds, and this is a result which uses characteristic 0. Yeah, thanks. Good. So now we can play a trick which is standard, but it's very useful. So assume that we are interested in a coefficient v, and we find a relatively projective object with a surjection on it, and we have a certain control on its kernel. In principle, this is a representation theoretic question. Yeah. Then we can lower the degree in the relative x by replacing the coefficient v by the coefficient L, and this is of course a long exact sequence argument. Yeah, so we use the long exact sequence. Since this here is relatively projective, it vanishes here because it's relatively projective. So the connecting morphism becomes an isomorphism, and we can gradually lower here the homological degree, and we can even go down to 0 to something that is computable. And in the end, what we need to understand is how we find such surjections from relatively projective objects, and how to compute the kernels and then compute tensor products. But all this is up to the knowledge what are relatively projective objects. This is representation theoretic computation. And so I'm not going to explain this here in full detail, because this is again a short exact sequence argument where you get here subjectivity and you have a control on the kernel. Yeah, so these are okay. So now you can prove more things. So for example, in our setting, the tensor product is exact. These are rigid categories. You can show that relative projective objects form a monoidal ideal. This also uses heavily rigidity. And then you can show that under also for the X, a dual object behaves as you know it from the home. Yeah, so we have to prove this, and in this way we can juggle around objects from the covariant to the contravariant argument, which is of course very convenient for computations. So, for example, we can do the following computation. Yeah, so we take allowable short exact sequences in Z of f. Then we want to focus on the monoidal unit, because somehow you feel that if you know a lot about a monoidal unit in a monoidal in a monoidal category, you should be able to do a lot. And this will come up in the last part of the talk as well. So suppose we have such a surjection from a relatively projective here, and similarly here for our coefficient object. Then we can get the following dimension formula for Davydov-Yetter cohomology. It is the dimension of, well, these are objects in our Drinfeld center-like category, K and M. K is the kernel here. And M is an object which is, of course, since we have to compute tensor products, it's cumbersome to compute it in high degrees, but it's in principle a representation theoretic computation. And then P enters, that's again, that's the kernel here, and again some home. And the way you prove it is by using all this lambda. So we are first using the long exact sequence to decrease the degree. Then we are getting here, because we use this long exact sequence, we are trading V, and then we are using the duality to put it to the other side. Then we apply the trick again, then we are using the duality and so on. And in this way, you are playing on until you have in the very end some representation theoretic expression. Well, so this is a computation in representation theory, and you can do explicit computations. And if I should say you can do, then I shouldn't say I can do it. I should say that the really hard computations have been done by Mathieu Fetch, and he did a really remarkable job. So I should give him the credit for this, not only for the computations, but quite particularly for the computation. And so we did it here for the small quantum group, admittedly at a small root of unity, but this could be done by hand. And we computed also higher cohomology groups in using gap. So for example, you find here that this small quantum group has 3 deformations of the associator, and they are not obstructed. All this can be done. These are explicit computations, and they are quite feasible if you use tools like gap in the end. Yeah? So without gap, it's getting a bit too long. And you will find the gap code on Mathieu's page.
This I here is just the complex number I.
This is the complex number I, and it stands for the 4th root of unity. Yeah, so that's why I said I'm doing this at a very small root of unity. And we might agree that I is a small, yeah. Okay, good. So let me go to the last part of the talk. So I'm realizing I'm a bit quicker, but I started also somewhat earlier. I want to have an additional tool. So you see, what is my basic idea? So here's the adjunction we have been discussing. That's our generalization of the Trinfeld center for a given monoidal functor. And we want to compute things for Davydov-Yetter or relative cohomology over here. But typically, we know quite well here this adjunction, which is the standard Trinfeld center for C. And in particular, if we want to study several of these Fs, because we want to study, for example, several module categories, then it would be great to do most calculations over here and then to transport the relevant quantities. Well, we are given a functor here, and actually this functor has a lift. It has a lift in a very obvious way, because if we are given a half braiding here, for an object here comes with a half braiding, applying the functor gives us this type of natural transformation, natural isomorphisms obeying a hexagon. So we really get an output here. This is a lift. And now you have to sit down and work, and I won't do the work here. What you can show is that if you start with a relative projective resolution over here, you get a relative projective resolution here by applying F. This is handy because once you have found some relative projective resolutions here, you can transport them and use them for your problem that depends on F. And what's even better, that's a theory of lifting adjunctions, is that if we are given a monadic adjunction, so if F has a right adjoint, then G, then we can lift it and we get also a right adjoint here. And actually I should have written R here, so this is a typo. Yeah, so we get a right adjoint, which is of course a functor from here to Z of C. Now what can we do here? If the setting is correct, so which means that C is finite and rigid, and D has a right exact tensor product. And I'm skipping here for D things like rigid, because we want to study module categories, and module categories are functors into endo functors of a category, and there's no reason why these endo functors are rigid. So this is deliberately weakened here in this way. Then you get, if you have here a right adjoint lifting, which was the functor I have discussed here, then Davydov-Yetter for a functor F can be written down in terms of Davydov-Yetter for the identity functor. So that's playing in the central monad in the setting we really know best, with coefficients which are, one coefficient stays trivial, and the other one is an object in Z of C, which you can compute using the right adjoint. Okay. So in this way, you can again sit down and transmute cohomological questions into representation theoretic computations. And the important thing I should highlight here is that in order to do this, you just need to find a projective cover of the monoidal unit of the Trinfeld center once, and then you can do your computations. That's of course a big advantage. And so in this way, you can compute various things. And I want to give you one sample computation, what this coefficient object looks like. So if you want to, for example, investigate deformations of braidings, then you need to get, well, in this case, we had a tensor product endowed with a monoidal structure. So you need to get an object in the Trinfeld center of C box times C. And I'm identifying the Trinfeld center of C box times C, and the linear product of the Trinfeld centers, that's where I need perfect. And you're getting an object here, which is a coend. This looks already nice. It's getting even a bit nicer if you now do this for module categories. It's not completely written up yet for various reasons. Then you will see if you are deforming the mixed associator in module categories, you're getting an object in the Trinfeld center, which is well known. Namely, it's well known in the following sense that deforming the mixed associator, well, the mixed associator in CFT terms, these are boundary OPEs. And what you are getting as the coefficient object is exactly the object of bulk fields in a conformal field theory. So this should be the starting point of a really nice mathematical physics story where you can understand why deforming CFTs, which would be deforming module categories, can be expressed in terms of bulk fields. That's what physicists are doing all the time in a very formal way by adding terms to the action. And the hope is to understand this. Of course, this hope is a bit too early, and there is a big problem here. I was working just with finite tensor categories. The tensor categories we need in the applications are pivotal tensor categories. Yeah, so also the module categories are pivotal module categories. That's quite important to work in the end with sum-oriented TFT, and we are not at this point. And what I should say is that there is a generalization which works very well in the pivotal setting, and that's the topic of an ongoing master project. There's a generalization of monoidal categories, which are where you drop, of rigid categories, where you drop rigidity and replace it by something weaker. The Grothendieck-Verdier categories, and Gregor knows a lot about them. So in this case, you can endow also the functor category with two tensor products. So there's a day convolution, which is defined in terms of coend. There will be also some tensor product defined in terms of an end. We shouldn't call it night convolution because day was a person. Yeah. And what you can show is that if you are now in this setting, you can study Frobenius algebras. Frobenius algebras will be exactly Frobenius monoidal functors. And now we are in a context where you deform Frobenius algebra, so we are back to business. So that's the starting point of this story, but this story isn't worked out, so I can't tell you about it. But this is definitely something that will work out. And then there is, of course, a question about deforming also the underlying categories. Yeah, so that's work in this direction exists. So in the group of Wendy Lone, Violeta Borges-Marquez, she has a complex which contains the Davydov-Yetter complex as subcomplex. It's a double complex. So in principle, it's clear how to write down double complexes or even higher complexes. The question is, to what extent do we have computational tools of the type on which I was focusing in this talk? So the point is, you don't only want to write down complexes, but you want to be able to evaluate them. And we can evaluate them so well that we produce, for example, Mombelli's results on deformations of module categories for Sweetler-Hopf algebras and Taft-Hopf algebras explicitly at the level of infinitesimal deformations. So in a sense, this conference is called Spaces of Tensor Categories. Yeah, so here the space of tensor categories is parameterized by the formal disk, but the formal disk remains a very interesting space. Thank you.
Any questions?
Yeah, so that computation for UQSL2,
Yeah.
where the third cohomology is three-dimensional, so it represents the deformations of the associator of
Yeah.
a category, right? So it's three-dimensional. Are these deformations actually known